Hello everyone, my name is Archita Agarwal. I'm a PhD student at Brown, and today I will talk about my work on encrypted key value stores. This is joint work with Seny Kamara. So I'll start with a brief introduction. Then I'll talk about the technical work on key value stores, and finally I'll end my talk with some future directions. So these days, the entire world is running on distributed systems, right? All the big companies have their infrastructures built on top of distributed systems. So almost all the apps that we use today, they use these distributed systems. So for example, Amazon's Cart or Facebook's Messenger or Google Drive, and there are so many other apps uh, which use distributed systems to store data. And as you can see from these examples, all these systems, they store very sensitive data about us. For example, they store our sensitive photographs, our health records, email data, geographical location, browsing history, and so on and so forth. But these days, what we are seeing is that these systems are getting breached on regular basis. For example, there was a breach at Facebook that leaked our photographs. Then there was a breach at Capital One, which leaked our credit card and social security numbers. Then there was also a breach at Quest Diagnostics, for example, which leaked our health records. So this is very serious, right? Um, so the question is that if I'm storing sensitive data in these systems and I want to prevent these breaches, what can I do? So, well, one solution is to use cryptography, which is one of the best tools we have to prevent certain kinds of data breaches, and we can integrate cryptography into these existing systems in some way. So I'm just talking about like certain kinds of data breaches, not all, but cryptography can definitely prevent some of these data breaches. So in this talk, I'll talk about how we can formalize the use of encryption in distributed key value stores. And it turns out that most of the systems that I talked about earlier, the storage systems like Amazon's Cart or Google Drive or Dropbox, they use distributed key value stores as their building block. So, because these key value stores are such a basic building blocks, so if we can somehow get encryption in them, we can then build all sorts of privacy preserving storage systems on top of them. So this brings me to the next part of my talk on how we can design and analyze encrypted key value stores. And here is a detailed outline of my talk. So let me start by explaining what are key value stores in detail. So key value stores are essentially these distributed and decentralized systems that are used to store and retrieve data to and from the servers that can be spread all across the world. So these are servers, and we'll be storing data in these servers. To support then data storage and retrieval, key value stores support two operations, get and put. Put is used to store data, while get is used to retrieve data. And in particular, put takes as input a key value pair, and it stores this pair on one of these nodes. Then get takes as input a key and retrieves the value that is associated with this key back. And for fault tolerance, what key value stores do is that they replicate our key value pairs on multiple nodes instead of just storing this key value pair on a single node. So for example, let's say in this case, if I want to store this pair, instead of just, let's say, storing it on one node, I will replicate it on multiple nodes. Here my replication factor is 3. And since data is replicated across multiple nodes, these key value stores employ some sort of synchronization mechanism to keep the replicas consistent with each other. And in distributed systems literature, there is a whole spectrum of consistency notions. Some are weak, some are strong, in the sense that strong ones can make a write instantaneously visible on all the replicas, whereas the weak consistency notions might take some time in getting your replicas in a consistent state. So, a read, if you do a read operation before, let's say, consistency is reached, this read operation can return different values. and the set of possible values that it can output depends on the kind of consistency guarantee that your key value store is providing you. And we'll see later in the talk that this notion of consistency, which is clearly important for distributed systems, also has an impact on security. Okay. So, apart from these get and put operations, these key value stores, they also support a routing protocol, which essentially is a communication protocol that nodes use to talk to each other, right? Because nodes are not just in one place, they're spread all over the world. So they need to talk to each other, for which they use this specific routing protocol that comes with key value store. And now for the rest of my talk, instead of calling these things as keys and values, I will call them as labels and values. And the reason is that in cryptography, key is reserved for cryptographic keys, so I do not want to create any confusion. So I'll be calling them as labels, so label value pairs. Okay, so now let us see an example of a consistent hashing based key value store. There are a lot of key value stores that are based on consistent hashing. For example, Dynamo used by Amazon, Cassandra used by Facebook, or Voldemort used by LinkedIn. They all are based on consistent hashing. So these CHKVS, as I would call them, they have a logical address space A that they organize in a circle. So just imagine these addresses as some bit strings of certain length. So for example, here I have showed A to be a set of all bit strings of length 5. So then starting from 0, arrange them in a circle. So then 0, 1, 2, tuck, 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 all the way till 32. So at setup time, this CHKVS outputs 3 hash functions, H1, H2, and H3. H1 hashes node IDs to addresses. So you can imagine that you have your nodes, which can be anywhere in the world, but then they are given a spot on this logical circle. So all these are nodes that are given a spot on the circle. Then the second hash function, H2, hashes labels to addresses. And so does this third hash function, H3. It also hashes labels to node addresses. And I will later describe how get and put operations, they use H2 and H3. Okay, so all the nodes at setup time, they also set up their routing tables, which enables them to talk to each other. So there are two kinds of routing protocols that are most prevalent. The first one is a multi-hop routing protocol in which messages from one node will hop through small number of nodes before reaching their destination node. Whereas in zero hop routing protocol, all the nodes can talk to each other directly. So there are no intermediate hops. And I'm not going to describe how specifically these routing protocols work because they differ from one key value store to other key value store, and it's also not important for our purposes. So I'll just skip it, but just know that there exists a routing protocol for each key value store. Okay. So now let's see how put operations are implemented in CHKVSs. So let's say that a client needs to execute a put operation. So put, let's say L4V4. So the first thing it needs to compute is the front end node, which essentially will act as the client's entry point in the network. So here what client does is that it computes the front end node as H3 of L4. So it uses this third hash function. So and then after it computes the front end node, it forwards the request to that front end node. Then what the front end node does is that it computes the replicas for this label value pair, right? Because we need to store this somewhere in the network, right? So the front end node actually computes those replicas. To compute those replicas, it computes H2 of L4. So let's say it's this red point over here. But as you can see that there is no node over here, so essentially you cannot store this pair on this address, right? Because there is no node over there. So what the front end node then does is that it computes the successor of this address. And the successor is essentially the first node that you would encounter if you travel on this circle in clockwise direction. So for example, this is the first successor of this address over here. So this becomes the first replica of L4 and the value associated with it, which is V4. Then it also computes the second successor, which then becomes the second replica of this label value pair. And once all the replicas are computed, the front end node then forwards the request to all these replicas, and then these replicas finally store the label value pairs with themselves. Okay. Yeah, so this is the second replica, and this is the front end node. Sorry, my animations are a little bit out of order. So because we want to analyze the security properties of encrypted key value stores, we realized that the first thing we needed to do was abstract out its core components so that we can then use these abstractions in our mathematical analysis. And this is how we did it. We realized that a key value store implicitly defines four mappings. The first is an address mapping that maps nodes to logical addresses, and as we saw in our example for CHKVS, this address mapping is essentially H1, right? The second mapping is a front-end mapping that maps labels to addresses. Again, for CHKVS, this would be H3, right? This is what the client was using to compute that front-end node. Then the third mapping is a replicas mapping, which maps labels to a set of addresses. And intuitively, these set of addresses essentially represent the addresses of the replicas. So for CHKVS, this would be the successor mapping composed with H2, right? Because that's what we did. We first computed H2 of the label and then computed the successors of those hashes. And finally, there is a route mapping which takes in two addresses and returns the set of nodes that would fall on the path of these two nodes. Okay. So now that we have defined our key value stores and abstracted their components, the next step we do is start thinking about encrypted key value stores and how we can formalize them and study their security. So we use the provable security paradigm to do so. And as part of the provable security paradigm, the first step we did was to define its syntax, as in what do we mean by an encrypted key value store. So encrypted key value store, it consists of four protocols: gen, setup, put, and get. These three protocols, they are similar to that for plain key value stores. So the only difference is that now put and get would also take encryption keys, which would be used to encrypt our label value pairs. And gen is another protocol that clients would use to generate these encryption keys. Okay, so after we fixed our syntax, the next step was to define the security definition. So before that, let me just quickly describe our adversarial model. We consider a static and passive adversary. So this adversary hacks in some of these machines, and after he hacks, it's going to sit there forever and see whatever happens at these machines. So it's passive, so it's not going to do anything else, but it's just going to observe and try to gather as much information as it can. Okay. So the definition had the same flavor as MPC style definitions. So we think of two experiments, the real experiment and the ideal experiment. So in the real experiment, we are actually running the protocol. So all the get and put operations are really being executed. Whereas in the ideal experiment, we want to create a simulator which, using the leakage, can simulate a fake view. Right, so that these two experiments, they start looking indistinguishable to an adversary, right? And this leakage is essentially the information that the adversary will learn. Okay, and we say that if we can create such a simulator which can successfully fool the adversary, then our uh, EKVS protocol or encrypted key value store protocol is secure. So now that we have our syntax and we have our security definition, now we would prove that our EKVS construction meets this definition. So of course, the first thing I need to do is to describe this construction, which then will prove to be secure. Okay, let's see how the construction works. So the first protocol is the GEN protocol. It samples two keys, K1 and K2. K1 is essentially the key that we'll use for the PRF, and K2 is an encryption key. And GEN protocol then outputs both K1 and K2. So the put protocol takes as input a key K and a label value pair. It then applies a PRF on this label L to get this sort of PRF label T, and it then encrypts the value V to get this encrypted value E. It then gives this sort of encrypted label value pair T and E to a plain text key value store, which then essentially stores this sort of encrypted label value pair in the network, right? Then get works in a similar way. You have a key K and label L. So again, you apply the PRF on the label L to compute your T. Then you give this T, then you give this value T to the key value store, which then fetches the encrypted value E associated with T, and then you just decrypt E to get your V back. So let's look at its analysis now. So the question was that essentially now that your data is encrypted, now you're not storing plain text label value pairs, but instead you're storing sort of encrypted label value pairs. So what kind of security can you expect out of this scheme? So in our work, we consider two different settings, a single user setting and a multi-user setting. So in the single user setting, clients do not share their data with other clients, whereas in multi-user setting, they do. So in multi-user setting, they can be two clients working on the same piece of data at the same time because they are sharing data with each other, right? Whereas in single user setting, this is not going to happen. So at a time, only one client will be operating on one piece of data. So we show that in the multi-user setting, the EKVS construction that I showed earlier is L secure with high probability. And L is essentially the leakage and is equal to the operation equality, which is essentially when do the clients repeat their operations on the same label. So this is not revealing the label, but essentially when a query is repeated on the same label, right? So sort of the repetition pattern. The key thing here is that in this setting, we reveal the operation equality of all the pairs, irrespective of whether this pair was stored on good node or a bad node. However, in the single user setting, this can be improved, and we can show that the adversary will only learn about the operation equality of a subset of labels. And this subset is essentially determined by the properties of the underlying key value store. So in particular, we isolated three properties of key value stores which had security implications. We called the first property the balance, second non-committing allocations, whereas third the consistency guarantee. And we show that if key value stores essentially satisfy these sort of two properties and a certain notion of consistency, then it's possible to show that the leakage can be reduced in the single user setting. So at a high level, balance sort of says that with high probability, any adversary that is corrupted at most theta nodes should not see a label with more than epsilon probability. Okay, and we define this property of balance, this balance property using these four mappings that we had abstracted earlier for the key value store. So I'm not going to define this second property because it's much more technical, so I'm going to skip it. So the third property that we required was that the key value store should satisfy a certain notion of consistency guarantee, and which is read you write consistency in our case. And read your write consistency essentially said that clients should read their most recent write. So if they write a particular value, then they read it again, then they should read the most latest value that they have written. That's what read your writes consistency guarantees. So we show that if the key value store is indeed balanced and its read or write consistent, then encrypted key value store is L epsilon secure with high probability. So L epsilon essentially means that we are leaking only the operation equality of pairs that are visible to the adversary. That means that operation equality of pairs that are either routed by bad nodes or are stored by bad nodes. So the adversary does not learn the operation equality of pairs that are exclusively stored and routed by good nodes. Whereas in the multi-user setting, we were leaking operation equality of all the pairs. So in our work, we also wanted to check if there are key value stores out there that even satisfy the balance property that we required from them, right, to construct our secure encrypted key value stores. Because otherwise, what's the point? If this balance property is too strong and no key value store can really satisfy it, then we cannot essentially construct secure encrypted key value stores. So we show that CHKVSs, they indeed satisfy the property of balance. And here I'm showing you the values of epsilon, theta, and delta for the case of zero hop routing, but we can show similar numbers for multi-hop routing. It's in our paper. So again, you do not have to look at these numbers, but let me just give you some idea on whether these are good or bad. So asymptotically, this epsilon can be written as this, right? And it turns out that if we assign labels uniformly at random to row nodes, where row was the replication factor, so then the epsilon would be this, right? So this is the optimal epsilon that you could hope for because you're assigning labels uniformly at random to nodes. So if you compare these to epsilon, then there is only this extra logarithmic factor in this case, right? So this epsilon is not too far away from optimal. So therefore, zero hop routing CHKVS balances data pretty well. Okay, so this brings me to the end of the technical section. So I'll quickly talk about some of the future directions and some of the interesting problems that we can work on. So this work was particularly exciting because we have not seen these kinds of works before, which explored sort of the fundamental connections between cryptography and the properties in distributed systems. So for example, in distributed systems, we have seen works exploring connections between efficiency and consistency, while in cryptography, we have seen sort of works exploring connections between leakage and efficiency. But this third relation is new and sort of unexplored. And it'll be interesting to study this connection in more depth. So, for example, one thing is that one question is that are stronger notions of consistency better for privacy, right? Because we saw that in the single user setting, once we assumed read or write consistency and of course some other properties as well, we could show that we can reduce the leakage. So the question is that is this the case that by assuming stronger notions of consistency can we improve privacy as well? And if the answer is yes, so then can we use the same technique, same sort of assumption in multi-user setting to improve the leakage, right? And whereas if, let's say, the answer is no, can we show a lower bound on leakage in multi-user setting, that you have to leak at least this much in the multi-user setting, irrespective of what you assume about the consistency guarantees. And that will be all. Thank you.